Let's look at wind turbines. And you'll find this formula in the data packet for the energy of a wind turbine. And basically, this is the total maximum power available for a wind turbine to harness the energy. And what it becomes is it just becomes the energy of this wind. If you just imagine the air, a chunk of air that's a cylinder, if you can kind of picture this, right? The energy of that, basically the power is going to be the 1/2 mv squared of that wind divided by the time it takes that to go by, right? So if we do a little derivation, right, we get 1/2, right? The mass is going to be the density times the volume, right? I'll put a V with years on it, right? Times the velocity of the wind squared divided by time, okay? If we further mess with this, right, the volume becomes 1/2 the density, and then the volume is going to be pi r squared, where that's the radius of these things, right? If we measure this radius here, that's our radius, right? Pi r squared is the radius of that circle times some distance, I'll call it x, right? I'll call this distance x. They call it d, but I like calling it x, right? Times v squared, and then we divide that by t. Well, if you look at this thing, right, this is just the area, right? So if we just simplify this, notice that x divided by t is just another factor of v, right? So we end up with 1/2 rho, the area, which is the pi r squared, right, times v to the third, right? And that's the power available. Now understand that the ordinary wind generators don't stop the air. The air's still moving after it leaves, right? So they're somewhere on the order of 35 to 45% efficient, right? Which turns out there's a tremendous amount of energy in the wind, and so that's not too bad, okay? Yeah, so that's our formula. That's where it comes from. It just comes from the kinetic energy of the wind, and then you get another factor of V because that has to do with the rate at which that stuff is going by. Let's look at some example problems here. Okay, what maximum power can you get from a wind turbine with 8.2 meter long blades when the wind speed is 5.4 meters per second on the average? And this is the maximum power, right? Use the density of the air to be about 1.2 kilograms per cubic meters, right? So let's go. Power is 1/2. The area is pi times, that's the radius, right? 8.2 squared. Right, the density is 1.2, and our velocity is 5.4 to the third, right? Notice that this is, what are the units of this? This is meters. This is kilograms per cubic meter, right? This is meters per second. What are the units? It's like, oh my God, I don't even know. You could figure it out, right? I will have the units of watts. Okay, so let's plug this into the calculator. So I'm going to go 0.5 times pi times 8.2 squared times 1.2 times 5.4 raised to the third power. The right arrow, hit enter. And I get 19957.7 roughly watts. And that's the total available, right? Which is roughly 2.0 times 10 to the 1, 2, 3, 4 watts. Is what we would say, because we only have 2 sig figs, right? All right, so yeah, and remember, understand this is maximum available. The real efficiency of it is going to be something like 35% of that available one. Let's look at there's another type of problem that you'll see, so let's look at that. And that's when they tell you that the air is 7.3 meters per second here, but it's slowed to 6.5 meters per second by the hitting these blades, right? Okay, and so what we're going to do is we're going to go power in minus power out, right? So we're going to say power is power in minus power out, right? And this is power in. This is the power that we're sort of discarding, right? I don't know how else to say that. So it's going to be 1/2, let's see, 8.5 meters long. So let's see, so it's going to be the area is pi r squared times 8.5 squared, right? Times the density, this air is a little more dense. 1.3 times 7.3, and that's the in, right? To the third minus 1/2. Obviously, you could just factor everything out except the velocities to the third, but I don't want to confuse somebody. All right, times 1.3 times 6.5 to the third. And by the way, this is fairly realistic. This makes this thing about 30 or 40% efficient. All right, so let's try this. I'm going to go 0.5 times pi times 8.5 squared. Notice that that's the same for all of these guys, right? Times 1.3, and now I'm gonna be lazy. I'm gonna go times parentheses 7.3 raised to the third. Right arrow minus 6.5 raised to the third. Hit the right arrow. Okay, there we go. And I get 16,877. 0.06 watts, right? So this is how many, we have 2 sig figs, so it's going to be 1.7 times 10 to the fourth, 1, 2, 3, 4, 1, 10 to the fourth watts. Okay. And again, that'll make this thing's, like 35 to 45% efficient. Okay, or worse, possibly, right? So again, for these things, when they give you 2 different things, right? The energy that we're reaping is the change. So we got to do this to the third squared minus, or to the third minus to the third. Okay. Don't subtract the number and then raise that to the third, because that's not the same thing. It's not true that A minus B to the third does not equal A to the third minus B to the third. Your math teacher will experience a sharp abdominal pain if you do that. All right. We'll do another example problem here, but I'm going to stop this video for here.